Hello everyone. My name is Ishni Chadha and with Utsanshu Tomar, we are presenting our final project for data center scale computing, which is titled Distributed Stream Processing Platform. Our main goal was to design and implement a fault-tolerant distributed stream processing engine from the ground up, capable of processing high-volume, real-time data with strict correctness guarantees. In terms of specific accomplishments, first we achieved exactly once semantics by implementing the Shandy-Lamport distributed snapshot algorithm. Second, we built fault tolerance into the system. Third, we reached low latency performance, end-to-end latencies of about 10 to 50 milliseconds for stateless pipelines and 50 to 200 milliseconds for more complex stateful windowing jobs. Finally, we have a production-ready deployment on Google Kubernetes engine with high availability configuration, horizontal pod autoscaling, and persistent storage for state. Now I'll zoom into the software and hardware components. On the software side, the job manager, which is our control panel, is written in Python using Fast API. It handles job submission and validation and also acts as the checkpoint coordinator, triggering distributed snapshots. The task manager forms the data plane. There are worker nodes also in Python that execute operators such as map, filter, and window, and manage local state using RocksDB. For communication, we use gRPC and protocol buffers for high performance internal coordination, and Apache Kafka as a durable log for data ingress and egress, supporting exactly once delivery. For state and storage, each task manager embeds RocksDB for local operator state. PostgreSQL stores job metadata and checkpoint locations, and MinIO store checkpoint payloads durability, so state survives node failures. For observability, we use Prometheus to scrape metrics like throughput, latency, and lag, and Grafana to visualize these metrics on real-time dashboards. On the hardware side, in our GKE deployment, we run a 3-node cluster of N1 standard 2 instance. Each task manager has a 100 GB SSD persistent volume for RocksDB state, and each Kafka broker has 50 GB SSD for message logs. This setup gives us enough CPU, memory, and storage to run realistic streaming workloads. This is our architectural diagram. Tying these components together, at the top, the user submits a job via REST API exposed by the job manager. The job manager parses the job graph and uses a simple scheduler to map operators into task managers. It also acts as a central checkpoint coordinator. In the middle, on the control plane, the job manager communicates with task managers over gRPC, for example, to deploy tasks, send heartbeat messages, and coordinate checkpoints. On the data pane, task manager consume events from Kafka, process them using the configured operators, and write results back to Kafka or other sinks. While processing, operators keep their local states in RockDB, and periodically we snapshot that state into object storage like MinIO or S3. Underneath, we have PostgreSQL recording metadata such as job status and checkpoint location, and Prometheus and Grafana connected to all components to collect and display metrics. Everything runs on Kubernetes, which handles container orchestration, restarts, and scaling. So this diagram captures both the control flow, job submission, coordination, and the data flow, event streaming through Kafka and task managers with durable state. Now I'll give a quick demo of the running system. The full platform is deployed on Google Kubernetes engine, and for this demo, I'm using our web dashboard that sits on top of it. On this main dashboard, I'll start by clicking Start Demo. That spins up a sample streaming job, so events and metrics begin flowing through the platform. You can already see the live counters and status indicating updating as the pipeline runs. Next, I'll upload a sample dataset. Here, I'll select our demo CSV file that contains readings like city and temperature. First, I'll run an anomaly detection operation. I choose the anomaly operation, use temperature as input column, and set a threshold of 25. As the job executes, you can see in the output panel that each record is labeled as either normal or anomaly based on that threshold. Behind the scenes, this is running on a master worker architecture. A job manager is coordinating the job and checkpoints, and multiple task managers are executing the operator chains and keeping their local state in an embedded key value store. This system is continuously taking distributed snapshots so that if a worker fails, it can restore state and continue processing without losing or double processing records. To show that everything in the cluster is healthy, I'll switch to Prometheus. Here you can see that all of our components, the job manager and each task manager, are up and reporting metrics. This confirms that the monitoring layer is connected to every part of the system. Finally, I'll move to the Grafana monitoring dashboard. This is a consolidated view of the platform in real time. As the demo job continues to run, all of these charts are live and continuously updating, which gives us a very clear picture of how the streaming engine behaves under load and during operations. To properly validate a distributed system like this, we focused on testing and debugging it under realistic conditions. For testing, we built a comprehensive job suite with 9 distinct job types, including word count as a stateless baseline, IoT sensor aggregation using sliding windows, and stream join jobs that correlate multiple input streams. We wrote synthetic data generations in Python that produce 1,000 to 10,000 events per second, simulating IoT sensors, financial transaction, and click streams. This allowed us to stress test the system at high throughput. We also did chaos engineering. During active jobs, we deliberately ran commands like docker kill task manager 2. After these failures, we checked that the job transitioned into a restarting state and that once recovered, the output event count exactly matched the input, confirming our exactly once guaranteed. For debugging, we monitored Kafka consumer lag in Prometheus to stop bottlenecks when processing fell behind. We used checkpoint tracing in PostgreSQL to see which task failed to acknowledge the checkpoint, helping us find issues like network timeout or serialization errors. And finally, we did a visual validation by comparing real-time throughput on our React dashboard with the output from Kafka console consumer to make sure the data flow was correct end-to-end. Building this platform taught us several important lessons. First, implementing exactly one semantics is extremely suitable. Coordinating Kafka offsets, log DB state, and checkpoint metadata correctly is really the hard part of the system. Second, we saw how much Kubernetes simplifies resiliency. It gives us pod restarts, auto-scaling, logging, and rolling updates almost for free, which would be painful to reproduce otherwise. Third, back pressure propagation turned out to be essential for stable throughput. Without it, fast producers can easily overwhelm slower consumers and cause instability. And fourth, strong observability is non-negotiable. Tools like Prometheus, Grafana, and cloud monitoring were crucial for understanding what was happening in a live distributed system. If we were to continue this work, we would add job manager high availability on Kubernetes, implement auto-scaling based on Kafka lag instead of using a fixed number of task managers, optimize our ROX DB state schema and serialization format, and add a more advanced optimizer to combine compatible operators into pipelines similar to Flink's operating chaining. Thank you so much for watching this video.